This is already the fourth class that involved music. The first made the point that music was about periodic sounds, but then in the next two, it became clear that we hear more periodicities than those of the harmonics in the spectrum, and the more we hear, the more pleasant the sound. Everyone's heard this tune from the 60s.
I know I stand in line until you think you have the time to spend an evening with me. And if we had some...
Yeah, something's missing here. This is what's missing.
I know I stand in line until you think you have the time to spend an evening with me. And if we go someplace to dance, I know that there's a chance you won't be leaving with me.
Yeah, that. You put those two parts together and magic happens. The duet of Nancy and Frank Sinatra blew all the charts around the world in 1967. And in 2001, Robin Williams and Nicole Kidman did it again. Listen.
I stand in line until you think you have the time to spend an evening with me. And if we go someplace to dance, I know that there's a chance you won't be leaving with me. Then afterwards we drop into a quiet little place and have a drink or two. I go and spoil it all by saying something stupid like I love you.
Yeah. I know you want to keep listening to it, but there's a class, right? One about the chords, consonant and dissonant. And how are these explained by what we know today about the human ear? When the right notes are played together, something inside clicks. Somehow, we feel some anxiety, then some other notes are played, and it resolves. The composer gets to our feelings with a message that transcends the need for lyrics. That Something Stupid song was a hit even in places where English is not spoken. No wonder the ancients figured that music had to do with the gods. Psychoacoustics and physics have managed to explain some of the whys and the how much of all this, and that will be the subject of this class. We have already discussed one very simple finding from these studies. Music requires periodic sounds. A pure sine wave form is the simplest periodic sound. However, it soon becomes annoying.
I cannot take this much longer.
A complex periodic waveform, like one from a musical instrument, sounds pleasant for a longer time, and pleasantness seems to increase with its complexity. Let's start by introducing a new term, consonance. When several instruments play the same note, it is said that they're doing a unison. Representing the two instruments by its spectrum, here's what happens when they play a unison. Say there's an instrument playing a note at 440 Hz. Now there's another instrument playing the same note. A musician would say that a second voice is playing a unison dyad to the 440 Hz root. The second voice reinforces every harmonic in the root. The second voice is said to be perfectly consonant with the root. Remember the combination tones? Those that do not really exist, for they are only amplitude fluctuations and happen when any two pure sounds add up. Yet we hear them as true spectral components with a frequency equal to their difference. Those are the combination tones. Each spectral component creates a combination tone with every other component. All the combination frequencies match exactly the harmonic series. So the combination tones also reinforce the harmonics. The second voice is said to be perfectly consonant with the root. Both instruments blend and the sound is slightly louder. We now look at this in the table form. Harmonics of instrument 1 vertically. Harmonics of instrument 2 horizontally. And the combination tones? We only displaying 10 harmonics, for these being the ones us humans mainly hear. The 10th harmonics are at least 20 dBs below the firsts. Let's color the background to indicate sound intensity. The zeros indicate that the harmonics of the root voice are being reinforced by those of the second voice. Every combination tone matches the frequency of some harmonic. That's perfect consonance. However, no periodicity other than those of the original harmonics are experienced by the listener. In an octave diet, the second voice fundamental is played at twice the frequency of the root voice. Only half of the harmonics of the root are reinforced by the second. But the combination tones reinforce every one of them. Again, there's a perfect consonance and the same periodicities. It starts getting interesting with the perfect fifth, or P5, when the second voice is played at 3/2 of the root. 1 every 3 harmonics of the root are reinforced. Again, the combination tones reinforce every one of them. Very consonant. However, there are new periodicities that make it sound, really different. The perfect fourth, or P4, is called the inverse of P5. The second voice is played at 4/3, which is the complement interval to the octave. Yeah, I know I have to do better than that. Here's the perfect fifth we already know, from A4 to E5. If instead of E5 we do E4, we have the perfect fourth. Okay, we're back to the P4 table. 1 every 4 harmonic of the root is reinforced by the second. Again, the combination tones reinforce every one of them. As with the fifth, there are periodicities other than the harmonics. This is the major third, or capital M3. The second voice is played at 5/4 in the just intonation scale or 81/64 in the diatonic scale. Only one loud harmonic of the root is reinforced by the second, though the combination tones still reinforce the harmonics. Not so many reinforcements occur in the hearable area. Periodicities are farther from the fundamentals. Let's do one more. The minor third or lowercase m3. The second voice is played at 8/7 in just intonation scale or 32/27 in the diatonic scale. Only a faint harmonic of the root is reinforced by the second. Harmonic reinforcement is happening in a faintly hearable area. New periodicities are farther from the fundamental than in the major third case.
Those squares keep getting bigger and bigger. Good chord for the square dance.
Let's all square dance. Places all. Bow to your corner. Bow to your own. 3 hands up and round you go. Break it up with a do-si-do. Chicken in the bread pan, kicking out dough. Skip to Maloo, my darling.
We're just losing consonants, you idiot.
Sebastian, it was a joke.
No, it wasn't.
The intervals in the diets has gone 1/1, 2/1, 3/2, 4/3, 5/4, 7/8. As x and y grow in x/y, there's less and less consonants, and as this happens, it becomes increasingly harder for the sound processing mechanism in your brain to find periodicities. These are the diets in an octave. Listen. Tension keeps building. As Sakaguchi puts it, lack of consonance creates tension, which is released when it is restored. Now we need to introduce a term that's very confusing. Dissonance. It has been defined, redefined, debated, hated, and even loved during the past few centuries. In the Middle Ages, the tritone, which means 3 tones, was nicknamed the Devil's Interval for its dissonance. However, Leonard Bernstein makes the most dissonant interval sound heavenly in his Maria from West Side Story.
Just met a girl named Maria, and suddenly that name will never be the same to me. Maria, I've just kissed a girl named Maria, and suddenly I found how wonderful a sound can be. Maria.
Dissonance can be melodical, harmonical, musical, sensorial, acoustical, or interpretational, and I'm probably missing more than a few. But we will boil them down to a couple of them. Musician's dissonance and physicist dissonance. Musicians, they're regarded as the lack of consonance. It plays with our moods. Most major chords are more consonant than their minors. Here's how the great Cole Porter puts it.
There's no love song finer, but how strange the change from major to minor. Every time we say goodbye. Goodbye.
For physicists, on the other hand, dissonants are beats within a certain band in the hearing range that produce a rough sound. The not a bit less great Hermann von Helmholtz stated that beats from 30 to 40 Hz produce dissonance. Listen. Almost 2 centuries have gone since von Helmholtz unveiled the nature of dissonance, but since then, many have contributed to a better understanding of it. For instance, Plumb and Leveled in 1965 proved that those 30 to 40 Hz of Helmholtz came quite near for pure sounds between 400 and 1000 Hz, but didn't hold beyond that range. The beat frequency for dissonance increased with the middle frequency of the dyad. Together with their empirical findings, they introduced the concept of critical bandwidth, which is the minimum frequency difference that produces a consonant sensation. Dissonance happens at 25% of this critical bandwidth. A good thing about this approach is that it goes well with the resonant mechanism of the basilar membrane in the inner ear.
And even better with the nonsonance of the acephalic monocardium of the probiotic protoplasm, right?
Got it. I must have sounded like Sebastian. Everything will come clear after explaining how the human ear works. The human ear, nature's spectrum analyzer. How about some anatomy? Skipping the external ear, it ends at the eardrum or the tympanic membrane. And here are its parts. Showing the insides of the middle ear, the internal ear, and the Cochlear.
This has more parts than a German car.
Yes, that's it. Medical specialists need to know all this Latin naming by heart. This allows doctors to understand each other even if they don't speak the same language. But for the physics of it, all we need to know is the hows and the whys. It is customary to explain the human ear in the direction of the sound. But for the hows and the whys, it might be easier to go inside out. So let us start with the cochlear in the inner ear, which is the actual spectrum analyzer, and allow a professional to describe it.
You're looking at an uncoiled cochlea containing a basilar membrane floating in endolymph. The organ of Corti, which contains the auditory receptors, sits upon the basilar membrane. Movement of the basilar membrane stimulates the auditory receptors. Notice 2 structural properties that determine the way the basilar membrane responds to sound. First, the basilar membrane is wider at the apex than at the base by a factor of about 5. Second, the membrane's stiffness decreases from base to apex, the base being about 100 times stiffer.
The middle ear manages to multiply and transmit the acoustical pressure at the eardrum into the cochlea, enough for producing cellular-sized movements in some part of the basilar membrane. There. Those microscopic movements are enough for altering the electrical potential of the hair cells, and this sends a signal to the brain through the cochlear nerve. The basilar membrane can be thought as formed by parallel vibrating strings that are shorter and tensed at the base, while longer and loose at the apex. Depending on the frequency composition of the sound, some strings resonate and some do not. Some nerves will carry signal and some will not. Whenever resonance is mentioned, then there's a bandwidth. And yes, that bandwidth has to do with a critical bandwidth that explains consonance and dissonance.
What's that thing that looks like a roller coaster? Childish. Those are the bass, treble, and volume controls.
Sebastian, those are the semicircular canals, whose primary job is to regulate balance and sense the head position, helping to ensure that vision remains stable despite motion, kind of your autopilot. This has nothing to do with hearing, so we are ready for the middle ear. The job of the middle ear is multiplying the acoustical pressure. Most explanations out there say that the middle ear amplifies, but amplifiers use a power supply to multiply the power of the signal, and no such thing happens in the middle ear. It is more like a gearbox that trades the big displacements of the eardrum for more force on the oval window of the cochlear base. Here's an animation showing the eardrum and the auditory ossicles, the smallest bone in the body, at work. This one is the Malleus, Latin for hammer. It hits the incus like the ironsmith anvil, and finally the stapes like the stirrup of a saddle. Tech people more familiar with pistons and levers may find this middle ear model easier to understand. The levers multiply the force by the same factor the displacement is divided. Then that force is applied to a much smaller area. All this multiplies the acoustic pressure by more than 20. And that will be all for this class, but there's one more thing. Sebastian was not totally wrong with out of a volume control, because there is one. Two little muscles called the tensor tympani and the stapedius contract when sounds are too loud, limiting the movement of the malleus and the stapes. Thanks to these, we do not destroy our cochlea when we shout. I know what you're thinking. Don't dare to say it. Well, it's that time. Time for the quiz. Here the answers will follow the question or problem, but hit pause and try answering it first. Say if it's true or false. When playing unison duets, there are no periodicities other than those of the harmonics. Okay, here's the answer. Remember the unison or P1 in table form? Notice that every combination tone matches the frequency of some harmonic, so there are no other periodicities. When playing octave duets, there are periodicities other than those of the harmonics. Answer coming? Again, the octave P or P8 in table form. Every combination tone matches the frequency of at least one harmonic of the root, and some may also match some harmonic in the second voice, so there are no other periodicities. Play a perfect fourth duet with a root of 330 Hz, and the lowest frequency that is heard is 110 Hz. Here comes the answer. Again, P4. The combination tones with the lowest frequencies are the subtraction of the fundamentals, the third and second harmonic, the fourth and fifth, and so on. So, it is correct. Complex periodic sounds are more pleasant than simple sounds with sinusoidal waveforms. The answer is, a complex periodic waveform, like one from a musical instrument, sounds pleasant for a longer time, and pleasantness seems to increase with its complexity. Now a simple sinusoidal sound.
I cannot take this much longer.
So the answer is, since the perfect fourth is the inverse of the perfect fifth, then the major sixth, like a C4 to A4, must be the inverse of the minor third, like A4 to C5. Here's the answer. Playing a major sixth, like C4 to A4, and then a minor third from there, that would be the interval A4 to C5, makes a complete octave C4 to C5. So, it is correct. For physicists, dissonance is just the lack of consonance. The answer? Knots in Helmholtz explained that beats within a certain band in the hearing range produce the rough sounds of dissonance. The basilar membrane is what is commonly called the eardrum. The answer? Not even close. The eardrum is the tympanic membrane that vibrates with the sound waves. The basilar membrane is inside the cochlea within the inner ear. It was the actual spectrum analyzer, remember? The ossicles in the middle ear manage to boost the power of the sound signal that goes into the cochlea. And here's what I have to say about that. There's no power boost in the middle ear. Same as the gearbox in the car that adds no power to the motor. It just trades displacement for more force. That's it. Most animations and drawings for explaining how the Cochlear works depict the sound waves as shown below. However, I have a problem with that representation, and there's one that especially hurts. That one. Can you tell what my problem is? Take a hint. Look up the data for speed of sound in gases and liquids. Okay, here's my problem. The wavelength, lambda, or the distance a wave travels in one period, is longer the faster the wave travels, right? Sound waves travel faster in water than in air, so the wavelength in the perilength of the cochlea, mostly water, must be longer than in the air of the ear canal. That's why I have a problem, especially with this animation. It suggests that the wavelength in the air are longer than in a watery media. And that's a big problem. There's also a quantitative problem with all those drawings. Let's take the highest frequency human can hear, 20,000 Hertz. The wavelength in the parallelism, 74 millimeters. Take one of the drawings, this one for instance. The Cochlear being 30 millimeters, the depicted wavelength in the parallelism must be then 3 millimeters. That would correspond to a totally inaudible sound wave of 494,000 hertz. That was my problem. Here's a flashcard for a teaching site on the internet.
Icicles of middle ear amplify sound vibration by lever mechanism, 2 decibels, area difference between tympanic membrane and footplate of states, increases force per unit area, 23 decibels, buckling of tympanic membrane, 6 decibels, total gain 31 decibels.
The decibel, or dB, is a logarithm unit. It is 10 times the base 10 logarithm of the quotient. Unless otherwise specified, it is a quotient of powers. For expressing the gain of amplifiers in dB, that quotient is the output power over the input power. Do those 31 dBs of total gain on the flashcard mean that the output vibration power at the oval window is some 1260 times the power of the tympanic membrane? And here's my answer. If the power of vibrations at the footplate of the stapes was greater than the incoming power at the eardrum, then the middle ear would have to be getting that power from somewhere to account for the energy difference, right? But no such power is coming in.
What about those 2 little muscles?
As already explained, those muscles are vibration dampers. No muscle can vibrate at sound frequencies. The meaning of those 31 dBs is that the vibration power into the cochlea is 1260 times greater thanks to the gearbox action of the middle ear. That is the interpretation. That tune hints that class number 8 is over. The nice background music for this class was written and played by Daniel Stolik, a musician, physicist, or physicist musicians, I could never figure that one out, that back in my student days was the head of the School of Physics. In my opinion, the best it ever had. Next class will be about sound waves in the open, reflection, refraction, diffraction, the Doppler effect, and more. Subscribe to the channel.